Yeah, Daniel's right here next to me. Daniel's ready. Hi, everybody. Okay. My name's Lee Vinsel. I'm one. Yep. Hi, everybody. My name's Lee Vinsel. I'm one of the two faculty organizers of the Department of Science, Technology, and Society seminar, along with Sonia Schmidt. And we also have a wonderful graduate assistant named Oliver Shui. I just wanted to say a couple things about the stream real quick. If you're on Zoom, it's probably still best to pin SocietySpeaker. You'll probably get the best feed. But you should feel free to experiment with your pins. In the room, it's very important that if we do follow-ups to a question where we come up to the microphone, that you come back up to the microphone. We had a couple times last time people just ask questions from their chairs, and then no one can hear it. Today, my colleague Daniel Breslau is going to introduce our speaker, and here he is.
Great, thanks, Lee. It's my pleasure to introduce our speaker today, Colin McMillian. Colin is an environmental engineer with a PhD in natural resources from the University of Michigan, and he works as a research analyst at the National Renewable Energy Laboratory, where he's published many papers and reports with his colleagues there. So much of the attention in energy transition and transitioning to an energy system that will not make our planet unlivable is the emphasis is on areas where we know what we're doing, like electrifying space heating and transportation, phasing out fossil fuels in electricity generation. But Colin's focus is on an area where we really can't say we know what we're doing. And you don't hear about it as much. It's a hard area, decarbonizing hard to decarbonize industrial processes. And Colin reached out to some of us a little over a year ago on his own initiative because he wanted to take some time, step back from his work as an analyst to get up to speed on STS, specifically the history of technology and socio-technical systems, recognizing, as he did, that industrial decarbonization was more than a technological problem, that it really involved things like the way organizations work and the way that managers think and the way that supply chains are organized. We found that he was really already up to speed on our literature. He was quite informed of STS literature in these areas. But since then, since we've welcomed him as an affiliate of our department, he's deepened that connection, the connection of the hard problem of industrial decarbonization with tools from our field. So from the title of his talk, it looks like he's going to put all of this together. And so let's move to Colin and his talk, Unveiling Industrial Uses, How Organizations May Mediate Decarbonization. Colin.
All right. I need to be able to share my screen.
You should be able to share now.
Oh. Great. I can only do one thing at a time. So, so thank you, Daniel, for that really nice introduction. Thank you, Sonia and Lee, for inviting me today to talk. I'm really excited to speak to you all. This has been sort of a journey for me, and I'm looking forward to sharing it with you all and getting some feedback because this is still a relatively new step for me, and learning how to talk about it and even putting together this presentation has been a bit of a challenge. So, but yeah, so maybe not for this audience, but in the energy analysis and climate change policy world, there are a lot more people these days actually paying attention to industrial process heat and how it's foundational for decarbonizing industry or eliminating greenhouse gas emissions from the sector. But I think if we really want to decarbonize industry, though, we should open up our framing of the problem quite a bit. And this is what Daniel started talking about, so it's nice to make that connection here. So I hope to provide some indications of new directions for research and opportunities for decarbonization. So let's get going with a quote. The freedom to reshape technology and society depends on the depth of understanding. So this, to me, is a powerful message and is something that's been guiding my approach to industrial analysis and modeling over the last few years. I'm going to base my presentation today around this quote because, for me, although it's short, there are many consequential aspects to it. Christopher Freeman was an economist. He was an evolutionary economist, was a driving force and first director of SPRU, the Science Policy Research Unit at the University of Sussex, and was also the founding editor of the journal Research Policy. We'll get back to this quote in a few minutes, but first I thought it might be helpful for getting a better sense of why I'm here now, giving this presentation, to quickly cover how my understanding of technology has evolved over time. So if you'll indulge me. Once I started at NREL, it didn't take long for me to see a figure like this, which shows the price per watt of solar photovoltaic modules over time and as a function of cumulative installed capacity. So over time, as we've installed orders of magnitude more of PV, the cost has dropped from over $100 per watt to less than 50 cents per watt. So these cost reductions have been incredible, and PV is now the foundational part of, or a foundational part of, reducing emissions from electricity generation. What struck me, though, is how some colleagues and other people were discussing these cost reductions, especially about expectations of future prices. You can fit a nice line to these variables and project them out into the future. People come up with rules of thumb, like if you double installed PV capacity, prices will drop by another 20%. But what started bothering me was that it seemed like people were treating PV modules as if they were marching ahead on their own. That there was just something about PV that meant if we just kept making more of it, prices would continue to decline. And that seemed to me that people had forgotten all the things that had happened over these 40 plus years. A lot has changed as you move along this line. And so it took me a little while to even figure out how this fit with what people had been talking about for a long time. But I eventually stumbled onto this collection of essays, which might be familiar to some of you. I admit that I only picked through it at first. These were completely different topics for me, and honestly, it was a little difficult for me to follow. But I'd say this planted a seed for thinking about technology in a whole new way. So in just a year or two later, at NREL, we started scoping the electrification future study. Now, this project imagined what a highly electrified U.S. economy might look like and what it might mean for the electric grid and its operation. I was in charge of thinking about the industrial sector and trying to understand under what circumstances different industries might electrify and which processes they could actually electrify. It seemed perfectly reasonable to me to first try to understand why industry electrified in the first place. And that line of research gave me more exposure to historical analysis and different ways of framing technology and technology change. More recently, there was the solar future study. This effort was about turning up the dial really as far as possible for all forms of solar energy. And for industry, this idea was even farther out there than electrification. So I ended up stumbling on the broader theories of how society and technologies co-evolve, why industries locate in certain areas but not others. I did want to mention, I guess, for students and any early career researchers, that the chapter that I wrote for this study is not the chapter that appears in the report. I was lucky that the lead of the overall study, who was also my manager at the time, was really supportive of the work that I was trying to pull together. And so the lessons I learned here, which I wish I had learned earlier in my career, is that you can learn a lot from failing and to not give up on research questions that you find interesting. And a lot of the material that I wrote for this rejected chapter, I'm still pulling from almost 3 years later. So really, the work that I did for the Solar Future study was my eureka moment. It's when I realized that decarbonization is very much this disruptive change for technology and society. And the largely techno-economic framing of the problem and the courses of research that I'm a part of in the National Lab System is sort of a shallow and narrow framing of the issue. And there's a lot of room to use the theories and tools of science and technology studies. Right. So yeah, today I'll be spending most of my time on industrial process heat. And this has been the focus of my research for the last couple of years. A really simple definition is that industrial process heat, or IPH, is the thermal energy used by manufacturers in their production processes. Process heat can take many forms, and it depends on what you're using as a heat source, the mechanism by which you're transferring heat, what kind of material you're heating. You can certainly think about molders pouring glowing hot molten metal as industrial process heat. But in the United States these days, a lot of the process heat that we use comes from industrial boilers like these that make steam and hot water. So not quite as exciting as glowing hot metal. So why do we actually care about industrial process heat? Well, we care about industrial process heat because of the vast amounts of energy and emissions it produces. Stepping back a minute, if we include energy emissions from electricity generation, the industrial sector as a whole in the US is responsible for about 1/3 of energy use and about almost 1/3 of CO2 emissions. As other people are pointing out, decarbonizing industry is really about decarbonizing process heat. Depending on whether you include emissions from purchased electricity, process heat is responsible for nearly half to nearly 70% of the CO2 emissions from manufacturing. So the other big chunk of emissions on these figures is labeled process emissions. And so I consider these to be related to process heat. These are the emissions that are the result of the way we produce certain materials. So for cement production, when you heat limestone past a certain temperature, you evolve carbon dioxide. For producing pig iron, which is an intermediate for making steel, you use a form of coal to pull off the oxygen atoms from iron ore, which also makes carbon dioxide. So I care about process heat for a few related specific reasons. I think it's a lot more fun and insightful to look at how things change over time. So let's take a look at the period of 1998 to 2022 to get a sense of what's been happening in the industry. The first thing we can notice is that there's some structural change in industry as an economic sector. These lines show how production in different energy-intensive and process heat-intensive industries have changed relative to 2012. Of course, we can see the effect of the 2009 financial crisis and some of the slow recovery of some, but not all of the industries. For instance, the paper products industry is still in decline. So we can also look at the energy-related direct CO2 emissions from industry. The dotted line is also an index, so it's relative to 2012. Again, we can see the effect of the 2009 financial crisis, although I think it's more interesting to note that it seems like the trend in decreasing emissions leading up to the crisis has largely been reversed since 2009. Our national climate goals are relative to 2005. And we are to reduce economy-wide emissions by 50 to 52% by 2030 and achieve net zero emissions by 2050. As of 2022, our direct combustion emissions from industry are almost back to where they were in 2005. There's been a 2% reduction. These data come from the Energy Information Administration, which are a little different from the data published by the Environmental Protection Agency. We use EPA data. Our industrial emissions are about 6% below or 17% below if you include the effect of the electricity sector below 2005 levels. But really, any way that you slice it, we really have a long way to go for meeting our climate goals for industry. Now, here's my primary reason for caring about process heat. So we've seen over these 20 years that there's been some amount of structural change in the industrial sector and economy, yet there's been really relatively little change in the types of energy that the sector uses. As a portion of total fuel used, biomass, which is by far the largest direct use of renewable energy by industry as well as electricity have changed very little. So I see this combination of different trends, or really sort of a lack of trends in these fuels, or maybe a constant trend. So it's clear to me that we're facing the embodiment of technology lock-in, of path dependency, of a really stable socio-technical regime. So there's a lot of different ways of describing how things have really not changed in terms of fossil fuel used for providing industrial process heat. And I think that is a problem for decarbonizing industry. All right, but if we look at how we focused on improving our understanding of industrial process heat over the last few years, it's been primarily from a technical perspective. And we do have a much better understanding from that perspective now than we did a few years ago. Much of this work has specifically been about improving the spatial, temporal, and operational characterization of process heat demands. In terms of what NREL has done, we started off by getting a general sense of the most relevant industries for process heat demands and where they're located. We then expanded that analysis to include all industries at the county level. And then we started to characterize the typical process temperatures for energy use, allowing us to visualize results like in this figure that show the cumulative process heat demand by process temperature. So maybe now with this information, we have a better understanding of what might make the process heat emissions from different industries easier or harder to abate or to eliminate. But let's return to our Christopher Freeman quote. I think that even the most robust techno-economic understanding of process heat doesn't reach the depth of understanding that Freeman mentions here, and that is critical for decarbonization. Elsewhere in the paper that this quote is taken from, Freeman is more specific about the areas of deeper understanding. The nature of change in technology. Is it an incremental change in an existing process? Or is it a change that affects the entire economy and society? Other areas of understanding that Freeman mentioned include the power of locking in processes, social and political conflict. So aspects of our very stable industrial process heat regime. I think this audience gets the implication of Freeman mentioning technology and society together. Overall, though, I think the interactions and dependencies between technology and society are something that we don't talk enough about for decarbonization, especially for industry. And I think we have a pretty shallow understanding as a result. Specifically, I think we should begin considering the social structures, dynamics, implications of decarbonizing the industrial process heat. I think when we do this, the problem becomes more complicated to solve. But that's okay, because I think at the same time we're identifying these thornier aspects. I think we're also revealing a broader and deeper set of possible solutions. So where do we go for this deeper understanding? I'd say the primary area that we have the shallowest understanding is in how and why industrial firms adopt and implement industrial process heat, or IPH, decarbonization technologies. In general, I think this is a product of a continued conceptualization of technology that excludes its social aspects. I don't think anyone here would argue that there aren't social aspects of how technologies are developed and used, or there aren't social forces that influence technology. However, I do think the true test of this understanding at the end of the day is the analytical framing and methods that are used. Are these social features being treated as core aspects of how we study technology, or do they show up as an afterthought, as a metric to be reported? So if you start from the position that there are important interactions to study between technology and society, a more focused question might be, what are the technical and non-technical user requirements of IPH adoption and implementation, and what do they imply for decarbonization technologies? So my NREL colleague Liz Vox and I set out and did semi-structured interviews of 13 different people in 8 industrial firms about the processes that were behind their adoption and implementation of alternative industrial process heat technologies. We asked 2 core questions in these interviews. One, how would you evaluate an alternative source of heat for your production process? And 2, in the past, have there been any significant changes made to your heating processes, like equipment replacements or retrofits? And then we had sub-questions in each of these areas that address the user requirements and associated metrics. the different individuals and groups that were involved in these processes, and specifically for implementation, if there were any problems and solutions encountered. I'll talk about the results of all these interviews in a few slides. But first, overall, I don't think we paid enough close attention to industrial firms as users of decarbonized technology. This figure is one way we can represent aspects of technology development, which includes perspectives of both technology producers and technology users. Users have been acknowledged as playing a part in technology development for many decades. But I think it's fair to say that US researchers who are concerned with industrial decarbonization have spent most of their time within this producer-centric model and have been concerned with efforts to develop new technologies and to bring them to market. But the policy landscape is starting to change, right? The Bipartisan Infrastructure Law and Inflation Reduction Act are providing funding for industrial demonstration and deployment programs. The Department of Energy now has an Office of Clean Energy Demonstrations. So I think we're starting to rediscover that users are an important part of technology development. What I think we're still missing, including in this picture, is how producers and users are connected. I think it's also fair to say that the general assumption is that as long as a novel technology meets some performance and cost threshold and maybe some market failures are addressed, that this technology will become adopted and diffused through the economy. So what do these assumptions about this unidirectional connection imply about technology and its users? But we have a rich body of existing research going back at least 20 years ago and earlier that explores the idea that technology systems can shape and be shaped by society. And more specifically, that frames technology adoption and implementation as social processes. One concept that has recently reemerged and has been applied to the question of decarbonization characterizes technology systems as either generic or configurational. This concept is grounded in examining the role that users play in technology development and innovation, as well as the need to incorporate technical and non-technical requirements for successful adoption and implementation. This relative comparison of whether technology is generic or configurational is based on three features: identity, systematicity, and system dynamics. But before we get into how those are defined, I want to return to our producer and user-centric models of technology development and how they're connected. We can consider this type of unidirectional connection where a technology is developed by producers and then passed over to users for adoption and implementation as being consistent with a generic technology system. So what makes a generic system generic? First is its identity, which has several aspects to it. To begin with, a generic technology has an established identity across all of its instances. So, for instance, when I show a picture like this, I think most of us would be able to identify what this technology is, right? So even something as kooky as this is still recognizable as a bicycle. Generic technologies also have standards for their function and performance, as well as existing markets for the system and the standard components that constitute that system. You can purchase an assembled bike, as well as individual components like handlebars, wheels, tires, et cetera, for that bike. You have standards for things like wheel sizes and tire sizes. Next, when we talk about a generic technology having systematicity, we mean that there is an underlying coherence that defines how the components relate and how they're integrated. And there's also the existence of standard plans for building systems and the provision of standard parts to realize those plans. So again, standardization is an important aspect of this feature, and there are connections to having a technological identity. You have standard parts that are integrated in a standardized, identifiable way. Going back to our bicycle example, you don't have to buy your bike pre-assembled. You can assemble it yourself. The same thing goes for more complex technologies like cars and airplanes. They have kit versions for those too, for the more adventurous of us. When we start talking about system dynamics, this is really where we get to the potential implications for decarbonization. And when we're talking about system dynamics, we're talking about pathways of technology development and innovation. So generic systems have this inherent logic that firmly structures development over time. And because of their established identity, standards for function and performance, and overall systematicity, innovation happens in this well-defined space. And last, technology suppliers can innovate independently of their application contexts, and they can use these sort of separate innovations to improve the overall performance of the system. So let's talk about bicycles one last time. I think it's safe to say that batteries and electric motors are the most significant recent innovation. And now you see motors on every type of bike: road bikes, commuters, mountain bikes. They even have recumbent e-bikes. And so an innovation in that component of the bicycle, this electric motor and the battery, improves the overall performance of bikes independent of their application. So let's go back to this producer and user-centric model for a second. So our generic technology follows this unidirectional path. Maybe there's some customization that happens during implementation, but the technology is largely standardized and ready to use. Now, what if to successfully implement a technology to get it into routine use? There needs to be a closer exchange of knowledge between technology providers and users about the technical capabilities and how they match user requirements and contexts. So this information exchange might need to happen even when a technology is in its development phase. And also, what if the implementation stage is the primary vehicle for learning processes, a learning by trying? Knowledge here is fed back into the adoption process, as well as during the development and manufacturing of the technology itself. So these features are characteristic of a configurational system, which is at the opposite end of the spectrum from a generic system. In terms of our three features: identity, systematicity, and system dynamics, configurational technologies have a much more loosely defined identity. These are ad hoc systems. To go along with that ad hoc identity, configurational technologies lack systematicity. The overall shape of the technology system is defined by the particular application and its contingencies. It's not possible to have an effective solution that is fully formed in advance without knowing all of these different requirements and contexts. Finally, for system dynamics, the technology development trajectory is much more uncertain because this innovation space isn't as clearly defined. And also because configurations need to be built up based on all these user requirements and local contexts, the greatest opportunity for innovation occurs at the level of the whole system and when it is implemented. So James Fleck coined this term innofusion to capture the combination and sort of collapse of the innovation and diffusion processes. So when we went back and analyzed the interview transcripts, it became pretty clear that industrial process heat technologies could be viewed as configurational, and that they lack an established identity across instances. They are built up based on user requirements and local contingencies, and they have uncertain system dynamics when it comes to decarbonization. I wanted to quickly walk through some of the quotes and other examples that I think best demonstrate the configurational nature of IPH technologies. So first, their identity. So we had interview EA12 that mentioned that, I mean, every plant is different because it makes different products. It has different configurations, and it might have different technologies. You might have different ages, so you have to look at it a plant at a time in order to determine what's the best transformation or change that you need to make. According to interviewee A8, the company as a whole has embraced the understanding that, like, we're moving away from traditional fossil fuel generated heat. It's a very local and a very site-specific answer to that question based on local resources and local things. I think right here we have some initial strong evidence that understanding user requirements and contexts play a critical role for IPH decarbonization. I wanted to mention one more aspect of user requirements that I thought was interesting and involves the interaction of sort of the technical and organizational and non-technical. So during their interview, A6 said flat out, we're under so much pressure when it comes to production that if you give me a solution that requires the factory to shut down for a week, you have not given me a solution. So it wasn't clear where in the firm this emphasis on not disrupting production was coming from, but it was a significant non-technical requirement for the firm and for this facility. So under the firm's current organizational climate, this requirement was setting the stage for what sort of alternative process heat technology could even be considered. But as big of a factor as it was for A6, this idea of disrupting production wasn't mentioned in all of the interviews. In fact, interviewee A7 had a different framing. They said, but usually, we do have this commissioning period where we try out the equipment, test it out. So there's a big commitment from the business to allow this commissioning period because they're not going to be producing. So there is this pressure to maintain production, but it's tempered possibly by the understanding that a temporary disruption in the short term is important for long-term success. Or maybe conversely, there's so much pressure to produce that the firm has dedicated resources to be able to minimize that potential for disruption. But how did each of these firms get here? Why is the prospect of shutting down production a showstopper for one, but not for the other? We can start to dig into the technical and non-technical features of these firms to start to understand a little bit of what might be going on. So these firms are in different industries and use heat in different ways. A6 is part of the food and beverage industry and uses boilers for steam heat. A7 is part of the non-metallic mineral product industry and uses direct heating from combustion. A6 never mentioned any regular shutdowns for maintenance or commissioning periods. A7, in addition to commissioning, mentioned that the firm sometimes adjusted production based on fuel prices. So they might actually be used to some sort of variability in their production. And more broadly, A6's firm was pretty new to having corporate emissions goals, and they weren't previously focused on climate change. A7's firm was similar in that they had only pretty recently set emissions goals for 2030. But the interviewee mentioned that the firm had this concrete roadmap for reducing emissions that they felt really confident in, and they felt like corporate leadership was really embracing ambitious projects. So again, I was struck by how these non-technical requirements could interact with technical ones. I also think this is a good transition from user requirements to systematicity or the overall shape of configurations. So these configurations have to be built up based on contingencies of their application. And here's what I think is a good example of building up a configuration. So we had one interviewee whose firm and organization were already thinking in detail about adopting hydrogen as a combustion fuel. I think it's also important to point out that this is a firm that is actively involved in hydrogen R&D. So I would say that they're already thinking more critically about hydrogen than other firms might be. The interviewee walked us through what adopting hydrogen as a decarbonized combustion fuel might look like for the firm. So we're already operating under the assumption that hydrogen is available at a sufficient quantity and at a cost that meets the firm's financial requirements. The facility might also provide utility steam to an adjoining firm. So let's assume that this customer is okay with any changes that this firm is making. So according to the interviewee, as long as the hydrogen mix was below 40% of the overall fuel mix, this facility was good to go. However, above 40% was a different story. At that point, engineering teams would need to get involved to evaluate replacing all of the burners in the facility. Other engineering teams would likely require that existing piping be evaluated and be completely replaced. Because the facility's air emissions would change, the air quality regulator, as well as the firm's environmental and regulatory organizations, would require a reevaluation of their existing air permits. And last, because of the facility's production processes, the health and safety organization would require an evaluation of safety procedures to account for having this much hydrogen on site. So we see all these technical and non-technical contingencies that are triggered as hydrogen is considered for this firm. As I mentioned before about system dynamics, without a clear identity and without systematicity, the innovation space is clearly defined, and technology development is more uncertain. So innovation happens with diffusion, this concept of infusion. So I think it's safe to say that of the firms we interviewed, those that were actively trying to decarbonize their process heat, many were struggling with this lack of identity and systematicity. And this showed up as uncertainty in the overall development process. Interviewee A6 captured this by saying, can't you, the DOE's national laboratories, just give us the answer? Guys like me, do each of us need to discover it for ourselves? Can't you just put out a paper that says, hey, if you got a natural gas boiler that's giving you like this temperature steam, the best way to decarbonize is by following these 5 steps. On the other hand, The development space is beginning to gel a bit for the firms that have been successful with adopting and implementing alternative process heating technologies. They are beginning to apply some of the knowledge to subsequent configurations. Interviewee A7 talked about this process and said, I know to electrify our plants it was, our engineers took almost 2 years of, okay, is this going to work for us? In the first electrification project, it's not just straight electric. They actually installed the capability of both electrical heating and natural gas heating as backup. But the subsequent electrification project, they realized, okay, we're confident with the electric heating elements. We no longer need a backup. So I consider this a case of learning by trying. And the innovation here was getting rid of the natural gas backup. And I think completely removing natural gas from the technology system is quite significant for decarbonization. There's one more perspective that was interesting to note. So this interviewee stated, I'll say there's a bias to looking for partnerships and sort of buying decarbonized energy in the future as opposed to buying the equipment that does it ourselves. So this is a completely different perspective than we heard from the representatives of the other firms we interviewed. I should also mention that this person also talked about that how unless there was something that emerged that had an immediate payback, the firm really wasn't looking to do anything transformational for reducing their greenhouse gas emissions prior to 2030. They were focused on purchasing renewable electricity and pushing energy efficiency, even though they have some really energy and emissions intensive processes. So if our new, deeper understanding for decarbonizing industrial process heat is to frame technologies as configurational as opposed to generic, what does that imply for decarbonization? First and foremost, it is essential to incorporate users' technical and non-technical requirements, as well as their contexts, for successful adoption and implementation. Along with this, learning processes and innovation occur during implementation and diffusion. Because it's not possible to build up a configuration prior to knowing these requirements and contexts, and there's little overall system standardization, learning is concentrated in implementing individual configurations and not with, say, sort of the separate manufacturing of individual components of the configuration. So I think these 2 points put into the question the framing of industrial process heat technologies as cross-cutting, or this idea that there's a natural transferability of the benefits of a technology across its different uses in different industries. We know that there's a lot of the US's process heat energy that's used for boilers, but that doesn't mean that decarbonizing boilers is a matter of electrifying everything, of using electric boilers or high temperature heat pumps across all of those instances. At the same time, though, I think our new, deeper understanding opens up new opportunities to accelerate process heat decarbonization. Because user requirements and contexts are so important, what are the ways that we can link users with technology developers to ensure that information is effectively transferred and is incorporated into a technology system? This could help develop identity and systematicity and move process heat technologies closer to having characteristics of a generic technology system. There are also opportunities to develop and transfer standardized knowledge about the full range of user requirements and contingencies. So I wanted to spend a little more time on this idea of a cross-cutting technology because I think it's used quite a bit in some of the other circles that I'm a part of. And one way that you can think about this concept is the idea that technologies, approaches, knowledge management, and infrastructure that are developed or deeply used in one energy production or demand sector could benefit others, resulting in synergies that amplify benefits, leverage resources, reduce costs, speed adoption, improve system efficiency, and conserve resources. As I mentioned before, industrial process heat is framed as cross-cutting because a lot of different industries use the same type of heating component, like a steam boiler, or they operate in a similar temperature range. But with our framing of IPH as configurational, we see that there's still this a critical need to incorporate individual user requirements and contexts, and it precludes this widespread adoption of a generic technology. And so just to pull on this thread a little bit more, let's talk about the electric motor. So surely if there was ever a cross-cutting technology that was used in industry, it's the electric motor. Though the quick history of the first electrification of industry is that mechanical drive went from this line shaft drive system that connected all movement in the facility to a central prime mover. like a water wheel or steam engine shown in the top figure, with various shafts, pulleys, and belts shown here in the bottom figure. I like to talk about how in the Baltimore Museum of Industry, they have an old-time machine shop that's set up with these line shaft drive system, and it's really quite incredible when they turn that sucker on. It's quite loud and quite impressive. So if anyone's up this way, they should check that out. So anyways, the system evolved to unit drive, or where electric motors are integrated directly with individual pieces of machinery. So this was a huge boom to productivity, allowed factories flexibility to completely rearrange their production layouts, led to increased production speeds, improved product quality, made maintenance easier, and so on, so on, so on. So if anything should be a cross-cutting technology, it should be electric motors, right? So we can look at how industry adopted electric motors overall over time. So we see this nice S-shaped diffusion curve in the early part of the 20th century. By the mid-1950s, nearly 70% of power capacity was electric motors. So that was just up from a few percent in 1899. But if we start looking at subsectors, we see there's some slightly different adoption patterns in different industries. Like for the rubber industry, it really took off after World War I, for example. Other sectors really lagged this average. The lumber and paper industries were two of the very last subsectors to electrify. And then you have a sector like printing, which was the clear leader in electrifying machine drive. So by going after a deeper understanding of what's happening in the adoption of motors for machine drive, we see there's about a 50-year gap between industries that adopted the fastest and the industries that adopted the slowest. And for me, this is something that's really important to think about in the context of decarbonization. If we need to reduce emissions in a fixed amount of time, it could be valuable to understand why differences in adoption and implementation exist. And there's this additional and related question of why the printing industry was so quick to adopt electric motors in the first place. I'm not going to get into that question, but I did want to talk a little bit about the issue of different diffusion speeds. So Brent Goldfarb, who is a student of Nathan Rosenberg's, wrote a dissertation that included analysis of electric motors as a general purpose technology. And he was specifically interested in this heterogeneity of adoption and diffusion across different industries. He dove into the fact that there are even intra-industry differences in adoption. So even aggregating to printing industry hides differences in different types of printing operations and how motors are used. His focus was the different complementary technologies that he identified as being behind the different rates of adoption. How quickly industries adopted motors was a function of these complementary technologies that were needed to integrate electric motors into different production processes. Goldfarb also talked about who was responsible for developing these complementary technologies. Some of these didn't require any information about user requirements and contexts, and others appear to have emerged from developers that could specialize in certain industries. So to me, there are a lot of similarities here with the concepts of generic and configurational systems, how big of a role user requirements and context play, and what the interactions are like between technology developers and technology users. So I'm still thinking about how everything relates, and so I don't know how this is really going to turn out, but I did want to cover Goldfarb's work in a little more detail because I really haven't seen it mentioned much. So for newspaper printing, which quickly and widely adopted electric motors, new motors were geared to existing printing machines with little modification. The major hurdles were fuses. So I guess early fuses tended to blow without enough time to protect the motors as well as the printing machines. So now note that this wasn't a problem that was specific to the newspaper industry. Everybody who's electric motor and had fuses had this problem. And it didn't require any specific knowledge about printing processes. I think it's also interesting to note that unit drive adoption in newspapers happened pretty quickly after a very public implementation of improved circuit breakers at the US government printing office, which I think it lends support for more public support for technology demonstrations. So book and job printing electrified much more slowly than newspaper printing. For one thing, line shaft drive still had advantages relative to electric motor unit drive. There's something about how line shaft drive could be geared to several machines and actually worked well for distributing power to the types of printing presses that we use for books. There were two significant technology hurdles that needed to be overcome. First was this difficulty with automating hand-fed operations for the presses. Second was figuring out how to make unit drive for presses that required this fluctuating power, which the line shaft drive was able to provide. And last but not least, we have the paper making industry. As I mentioned before, this was one, if not the slowest industries to electrify. And this came down to the paper machine itself. Like the book printing industry, existing technologies still had advantages over electric unit drive. So paper mills were built on rivers, and water power continued to have advantages. The primary complementary technology hurdle was synchronizing speeds of the various paper machine sections. So paper machines have all of these sections that roll out the paper fibers and press it and water it. And so they had to synchronize the speeds of all those different sections. And the innovation of sectional drive had the most dramatic result of electrifying the paper machine. I thought it was interesting to note that you had these major corporations that were involved in this innovation. It was Westinghouse that first experimented, then abandoned sectional drive. It was General Electric that later captured most of the market. So let's get back to heat and to the present. I wanted to conclude with what I think will be an interesting and an important policy test for industrial process heat. And this approach is the polar opposite of what's been done on the national level in terms of decarbonization policy, which has essentially provided all carrots and no sticks. I recently learned through popular media that California's South Coast Air Quality Management District is going through the process of amending a rule for nitrogen oxide emissions from commercial bakeries. Essentially, by 2030, these food manufacturers will need to have transitioned to a zero-emission technology for baking. And there was a quote in the story that I read that caught my eye, and I think it really captures the configurational nature of industrial processes. So let's end with a quote also. Commercial bakeries do not use all the same ovens or vendors, and a one-size-fits-all approach is not possible. Rasmus Voners, Vice President of Regulatory and Technical Services at the American Bakers Association, said by email, "For oven makers, a key challenge is delivering equipment that can produce the same taste, texture, and appearance as their gas and oil burning counterparts." So again, I just noticed that this is sort of like a technology producer-centric view of the problem, but this is a technology forcing policy, moving these firms to electrify their baking operations. If you go through the comments that were submitted about this rule change, some of these bakeries are pointing out that electric technologies don't even exist yet for what they do. In addition to that, some firms have proprietary baking methods, which they aren't sure can be replicated by electric baking. They may need to even change the recipes and ingredients, and they're not sure how that will affect their final products. So I think it will be interesting to see how technologies develop for these firms and their processes and what the interactions are like with technology developers. There are other questions like how the technologies may or may not be translated to other geographic areas and applications, as well as how knowledge and solutions can be standardized and quickly transferred. So I wanted to acknowledge the industry representatives that agreed to be interviewed for this project. I'm also grateful to Blaine Collison, who provided a lot of guidance, and most definitely to my colleague, Liz Vox, who conducted the interviews with me and who did the hard work of transcribing interviews. So that's it. Thank you all so much.
Hi, everybody. Colin, that was great. I know we have one question on Zoom chat, but does anyone in the room have a question? Jack, go for it.
Hey, Colin, this is fantastic. I'm glad you left your email at the end because I'm gonna definitely shoot you an email. In addition to a PhD student, I'm also the Climate Action Fellow for the university, so I have some really localized questions for you. But one of the things I'm really interested in your discussion of system dynamics is how some of the social and economic influences create a pull towards certain systems and not others. And here I'm thinking of pulls towards greenwashing. So thinking back with the boiler examples, one of the major shifts was from coal to natural gas boilers. And of course, many institutions, Virginia Tech included until the 2020 Climate Action Commitment, counted natural gas as basically producing no emissions because all of them are hidden upstream, as opposed to coal, which is based on the burning of coal. And so I'm sort of, and they did this as a way to sort of play into demonstrating a sort of illusion of progress in the way that greenwashing does. So I was curious to hear, your thoughts on how we can grapple with this pull at the level of system dynamics, and how much you suspect that hydrogen is a similar move, especially given some of the interests in developing hydrogen.
Yeah. That is a great question. So first, I'll point out that in one of the interviews, one of the industry representatives was talking about their evolution from their coal boilers to natural gas, and it was interesting to note that that the engineers felt like natural gas was very uncertain, and they were worried about that, making that transition, and so coal was seen as this sort of known factor, and natural gas was this unknown, might not be as reliable. So it's interesting to see how things change. So yeah, I mean, I think it's so the hydrogen issue. I mean, is certainly one that I think is maybe more complicated than. Well, certainly more complicated than just the technical aspects of producing green hydrogen. It's not something that I have spent a lot of time working on outside of this project, but there's certainly I think a lot to the regulatory aspects of it. There's a lot behind sort of the existing infrastructure, and so I think there's sort of a little bit of maybe a path dependency going on here. I know of some work. I can speak to some work in Sweden and in Finland. There was sort of a couple of joint efforts going on there to produce hydrogen from electricity in Finland and use it over in Sweden, because Sweden is doing things in the industrial sector like hydrogen direct reduction iron making for green steel production, and also hydrogen for ammonia. But there was a technical report that was put together just recently that sort of went through these broader requirements for getting together a hydrogen system. And I think one of the things I remember reading was that there was no sort of institutional capability that they identified at the time to actually process hydrogen permits. So they hadn't actually even, the regulatory side hadn't even caught up yet in terms of having the permitting available. And so I mean, I think, in this country we have a lot of activity in terms of applications for these hydrogen hubs. I think there's, obviously in the new tax credits and everything that have gone to hydrogen. I mean, certainly there's a lot of pull for hydrogen, and I think there are a lot of issues that haven't quite been explored yet in terms of who else is sort of what other organizations are pulling along for that technology, but certainly from a process heat perspective, it's the companies that we talked to, they were pretty, I would say, on the whole, skeptical of hydrogen at this point. So a lot of them said, if you're going to use electricity to produce green hydrogen, let's just use the electricity in the first place and skip those thermodynamic losses there. There's sort of other considerations. So it certainly wasn't top of mind for these companies, and that for a lot of these companies, and certainly that could reflect the types of industries that they were we're representing. It's generally thought of as like a high temperature fuel for processes. But
just to interrupt for a second, Colin, could you turn your Zoom mic, or your Zoom, not your mic, but your camera back on for the stream? Thanks.
yeah,
Jack,
I
you
know.
can-
I've been trying.
I thought you had a question from chat. No, I just wanted to thank you for your answer. I think that makes a lot of sense, and that's a very measured response. I'll send you an email.
All right. Okay. I unplugged it, which I hear helps.
Looks like Barbara Allen is up next, and then I'm going to read a question from the chat.
Hi, Colin. I'm Barbara Allen. I'm a professor of STS in Northern Virginia, but I'm not in Northern Virginia right at this moment. I'm really excited to hear your work and to see that chemical engineers are now getting involved in sort of the STS side of industrial transformation. But I had a little different question because I've studied environmental justice of communities that live around sort of petrochemical plants for my whole career. And my concern is when you open the black box of this industrial process heat decarbonization, you have to think about what the losers in this scenario are doing. And there was a recent article in the Bloomberg News just the other day. It was titled, and I'm reading from my notes, Exxon plots gasoline to chemicals switch because of electric vehicles. And they're applying for a change in feedstocks and product runs so that they can produce more plastics, more lubricants, more high value industrial chemicals. So these, just because hydrocarbons aren't burned doesn't mean they're not bad for the environment. So as one pressure and positive story hits about hydrocarbons, are people in your field studying the sort of dark side that these companies are figuring out other ways to get their hydrocarbons into our consumer world?
Yeah, I mean, I would say that by and large, most of the research that I'm familiar with is more on the technical side of how to make that happen, and much less about sort of the issues that you raised. I know that Sonia, Daniel, and I are thinking about something for the plastics industry, and there's a report that came out just a year or so ago that calls plastics the new coal, right? So it's this idea of maybe we're fixing one part of the problem, but there's this whole, I come from an industrial ecology background, there's this whole sort of upstream aspect to it too. So I mean, I think for me, hearing I brought up that point about a company getting rid of their natural gas backup. I mean, I think it is important to remove that sort of infrastructure piece for companies, at least from the heat side. I will say also, I mean, I think I'm familiar with work at different labs that are looking at sort of plastics recycling and sort of how to capture plastics, and maybe, I don't know if work is going into, like, I know lubricants and motor oils are recycled, maybe they're also combusted, but I don't know if that research is as emphasized as sort of the plastics recycling piece, but you see those issues connected in certain ways.
But I think that the point this article was making, and I've seen some other articles too, is that as they lose their market to sell gasoline, they're going to figure out something else to do with it. And what's the infrastructure for guiding that to some other place that's not destructive? And yeah. As STS scholars, it's good to look at the positive thrust of where things are going, but also looking at the pressures that it puts, market pressures on the losers in that positive thrust.
Yeah. Yes. Yeah. That is really an important question.
Or Cambridge, it is, have you seen the firms that have made progress on decarbonization build a Kepner-Trigo-like program that they market to make income back on the process? KP, as I knew it, was a troubleshooting framework for engineers that worked in a kind of different environments to find root causes of issues.
I'm not aware. So maybe, yeah, it's not something I'm familiar with. Maybe it'd be helpful to talk a little bit more about the folks that we interviewed for this little project. I mean, so these were people that were largely in sort of the corporate sustainability role, right? And so the paper that I'm scrambling to finish and get submitted talks a little bit about how these individuals are sort of at this junction of, sort of steal an idea, this mediation junction between sort of their corporate environmental goals as well as sort of different goals of different organizations that they're a part of. So they have to sort of balance what process engineers are asking for, as well as the finance department and procurement and everything. And so they're sort of at this intersection of trying to figure out all of these different user requirements. And so, I mean, one of the things that we really wanted to do for this project is talk to folks that were sort of on the production floor. And so some of the theory that we were working from says that you might have different layers of a firm, of an organization might see, and probably does see, technologies in different ways. And so there can be misalignments between these different layers of the firm that sort of shape how technology is implemented. So we really wanted to sort of work our way up and down to get different perspectives of process heat, but and talk with some sort of floor engineers or plant level folks, but that just didn't happen. There was a real hesitancy to use up those folks' time for interviews. I think that the people that we spoke with were very generous with their time, but also very aware of taking up the time for those production personnel.
Great. So I'm not seeing any other questions, but I'm gonna keep my eyes out. I got a question for you.
Yeah.
So I missed your policy slide. I had to step out, but I was just wondering. So when I listened to your talk, I found it pretty depressing. You know, like, because it's kind of like it just goes to how hard this is going to be, actually. And I think, like, I just recorded a podcast episode earlier today with someone who was looking at EVs and all the issues around EVs we're not talking about. I feel like whenever you put your finger down into one of these holes, it just you go to dark places, you know? So I'm wondering, like, with policy, like, is it too early to regulate, you think, because of lack of knowledge? Because I was thinking about, like, with what we did with cars in emissions in the 70s, which, you know, I know something about. And we just chose 3 emissions that we thought were causing smog and just told the companies, like, you're going to reduce these by 90% in 5 years, or we're going to shut you down. And they figured it out. I mean, it took more than 5 years, actually, right? So, I mean, I'm just wondering about, like, technology forcing standards. Like, just telling these firms, like, here's your date, figure it out, we will support you in any way we can, but just go for it. Or do you think it's way too early to even think about that?
Yeah, so, right, so I sort of consider my role here in coming from a very technical organization is to say, hey, this actually might be a lot harder than just getting the technology right. And so from my perspective, I'm not trying to be a downer, but I'm just trying to say that it might be helpful to know in ways that it might be very difficult to do this beyond trying to get the engineering or the sort of the technical aspects of these technologies right. So yeah, I'm trying to, maybe that doesn't come through the presentation as much as it should, but my hope in doing this work is to say, let's figure out sort of why it might be very difficult, and then see all these different points as ways that we can attack the problem. Because right now, if you're just worrying about the techno-economics, that space is, I think, a little constrained, right? So I think the slide that you missed, Lee, gets to your question. So this South Coast Air Quality Management District in California, they are doing technology forcing policy. So they are in the process of through nitrogen oxide emissions, essentially forcing commercial bakeries to electrify their operations. And so it is it is just a handful of types of baking equipment that they're focusing on, and it's only translates to a handful of bakery operations. But it is a very different approach than what we're using on the national level right now. So yeah, from what I've read from responses to this proposed rule change, the bakeries, these large industrial bakeries, it's not just mom and pop shops, but these large industrial food manufacturing facilities and their equipment providers, technology providers are saying, hey, we can't do this. This is too big of a lift. The technologies don't even exist yet. And it was interesting to also we talked a little bit about this in a previous question, sort of the infrastructure for hydrogen, but there's also this infrastructure piece for electricity, right? So in the interviews that we did, people talked about what size of an increase in load that electrifying a process might actually result in. And so people were saying that my local electric utility can't provide they don't have the generation capacity, they don't have the transmission capacity. Like, now that introduces all sorts of costs to electrifying this process that are outside of my facility. And so is that rolled into the cost of electrifying a process heat operation? And so those arguments, and it was interesting to see this back and forth between the air quality regulators and the bakeries. The bakeries were saying, it's not just changing the equipment inside the facility. The costs that you folks are saying that are quite reasonable actually might include things like getting additional transmission or capacity. And so yeah, it's interesting to see how the back and forth is evolving, right? And whether or not this little tiny test case for technology forcing policy, I don't know what's going to happen with it. So maybe these bakeries will figure out some great new technologies to use, and hopefully those will be translated to other bakeries across the country that are in areas that have existing zero carbon electricity generation, because that was also another requirement that these firms were interested in. They weren't looking into the future. They wanted to know that they weren't swapping their combustion emissions for emissions from electricity. So that greatly constrains where electrification is of interest to these industrial companies.
Hi, thank you. My name is Monami Haynes, and I'm also an assistant professor here at Virginia Tech. And I had a question following up on Lee's a little bit. And this is the question of eco-authoritarianism. And I know it might come out of left field a bit, but I was linking, taken by that I think the interview you did about the pressure an organization is facing, and so stopping production is not a solution. And in thinking about these pressures, I'm thinking about other country contexts where these kinds of environmental standards are very much put into place and then and affected. And all these problems that you're talking about, I'm sure these other firms face, but they have to manage it perhaps to other unintended consequences. But and those sort of eco-authoritarian models, and I'm thinking of Singapore and even to a certain extent in Denmark. And my question is, do you think in thinking about these user-producer relationships, we also need to take political culture into account as well? Thank you.
Yeah, no, it's so I will say that a lot of the work that I've been doing recently was inspired by a paper that came out a couple of years ago that looked at the slow transition of heat decarbonization in Germany, right? And so and really that's where I was reading about sort of domestic and building heating technologies, and the authors use this configurational and generic system framework. And I thought, if these building heating technologies are configurational, then surely something in industry is, that is sort of blows building heat out of the water. And some of the haven't followed it as much, but I know that the European Union has targets for renewable heat, sort of like the fraction of renewable electricity. They also have targets for what fraction of heat is from renewable sources, and actually heat pumps are included as a renewable source. But around the time that I was reading a little bit about German legislation, I think I also could be getting this part wrong, but I thought they had at least been able to move new building standards of efficiency to the point where it precluded installing like a gas or oil boiler. So it was moving people to renewable boilers for their building heat. But more recently, I caught a newspaper article that said there's been a real pushback in terms of targets for replacing boilers in existing buildings and houses. Like the public has just been sort of up in arms about that from a sort of a domestic heating side, and so there's you think about that, and then in the U.S., I'm aware that there are sort of local jurisdictions that want to ban gas hookups, and so that has led other states really to preempt that and say there's no way that a local jurisdiction can say that you can't have natural gas hookups. Like that's you can't do that. So I think I've seen a map that sort of points out all of these different states that have gone down this road, and so yeah, I mean it is definitely there are a lot of sort of between nation differences in what's acceptable for regulating emissions from heat, and certainly there are within subnational differences as well. Yeah, sorry.
Right,
I hadn't had not heard of that term before.
Eco-authoritarian.
Eco-authoritarian.
can I say? Yeah. Thank you. Thank you for your amazing presentation, and I'm very happy to share your insight today. And actually, I'm the philosophy guy, so my question is gonna be like a little bit complicated, but Yeah, and also like a little bit similar to the former question, so I'm just worrying about it. But my master thesis was on the interaction between technology producers and technology users. And at that time, one of the things I was most concerned with was, that the impact of the new like brilliant technology has a very so powerful, and also the giant companies develop them has so like very big political power. So sometimes they just don't want to let us to share our experience or experiment. And also, and some people just don't want to care about what they are doing and just want to let the technology march ahead. So, my question is like, what do you think is most important thing to create or start the culture of the configurational model you're talking about from the start point, like in this society? Yeah.
I'm not sure.
Right.
I mean, I think that's one of the things that I was starting to attempt, and I don't think I will sort of run out of time on this, but my semi-sabbatical I've been on, is try to understand, try to use what's happened in history as an idea of what might be useful for moving process heat technologies from this configurational standpoint to a more generic one. And I think there's a lot going on here, and I think one of the things that's been difficult for me to wrap my head around is that it seems like there's this we're in sort of this early phase of this technology. I mean, even though electric boilers have in these different electro technologies and solar thermal, I mean, all of these technologies have been around for decades, right? But in some ways they're brand new, and the use of them specifically for decarbonization is a new concept. So we're in sort of this like formation stage, which I think is in some ways a little similar to this early stage of electrification. And so I think maybe to really answer your question, I feel like I would need to go back to some of the primary sources of the papers that I've read on this early part of industrial electrification to understand what those interactions were like between the technology users and the technology producers, right? So, we have cases where it's really generic and it's made complete sense, and it was really easy to include an electric motor on something, and then you have really difficult problems to solve from both a technical and organizational perspective. And so I think one of the other things that's complicating that comparison, and other people have made this point, is that when you look back into the past, into like the Industrial Revolution and sort of these other areas, you have technologies that are like they're driven by this market impetus, right? And so now with decarbonization, this is largely like a public good and a public benefit. So how do we square sort of the difference in motivation at the moment for these different industries? So like having a culture of, I mean, I don't know. I feel like there are examples in the European context in different member states for domestic heat pumps, and so there's been a couple of papers actually that have come out of Finland, and I guess there's this culture of heat pump users, and so people in their homes they have these chat message boards, like, from the early 2000s, that they were really into figuring out ways to improve how they're using heat pumps. And now, Finland, I can't remember what portion of their heating is heat pumps, but it's huge. And there have been several papers that have come out in terms of looking at how users have really led the adoption of heat pumps and figuring out what the innovations are and how to improve their performance, and working with technology providers. So I don't know. That's hard to get that culture going to make that change. I think it's difficult, because also one last thing I'll mention. Sorry, I don't get to talk to many people about this stuff, so sort of opening up a bottle here. So the other thing that I'll mention is that there was one firm that talked about how they had no interest at all, and they didn't want any sort of detail included about this electrification project that they did, because they saw it as a competitive advantage. They wanted no details about what the changes actually were like. So they were more interested in talking about something completely different that they were working on with a technology developer. So there's also this sort of this aspect of competition between different firms, which I think you can say is not there for like households or sort of on the building heat side.
Great, thank you.
Yeah.
Hi, Colin. Yeah, I just have a question that sorry? Oh, I'm Daniel Breslau. You met me earlier when I, so, hi again. And so this case of the California regulations and the way that these bakeries were reacting to it, they're sort of also talking about their configurational technologies and maybe emphasizing, the uniqueness of their processes as a response to regulation. So it makes me wonder if, the other industries you talk to, if they're also, if they have a good motivation to emphasize how unique their processes are, they know that it's just a matter of time, that they're going to face more scrutiny, possibly more regulation. They know they're getting a fairly large subsidy because they're able to socialize the costs of the emissions that they produce. So does that go into, or would that change your interpretation of your interviews to also see how they're really trying to manage the political environment around their activities?
Yeah, I can say that so these interviews happened before the Inflation Reduction Act legislation was passed, right? But it was sort of I think on the horizon, and these firms were aware that it was coming, and I think there was some anticipation about the financial incentives that that might be on the table. So people were aware of that. There was no recognition that any other type of regulation or legislation was on the horizon. And yeah, I didn't have any. I don't remember any indication that the companies sort of talks in the same way that these California bakeries are talking. So yeah, I think just the regulatory approach is quite different in those two circumstances so far.
I just wanted to add that I think the automakers said they couldn't do it until they did, right? And it was really important for the federal government actually to build a surveillance program to look into these companies and actually check their lab results to prove that they could. And so I think we have to think about like the political, how you build kind of knowledge around this stuff. But I think that's it. That was really wonderful, Colin. Thank you so much. And yeah, thanks everybody for participating. Colin, I'm looking forward to this thing you're going to do with Daniel and Sonia. And so hopefully, I'm sure you all will be letting us know about it as you put it together. So it sounds really exciting. Thank you again.
Thanks.
Bye.
Bye.